Section 6.2, Imaginary and Complex Numbers. First, the definition of an imaginary number. It's the square root of -1. So we're going to fill out this table here and then do some examples, some fairly relevant examples right here. I is just going to be I, but I squared is I times I, which is the square root of -1 times the square root of -1, or the square root of -1 all squared. And we know that the square root and the square, they're inverse operations, so those things cancel out, and we're going to get I squared equals -1. Okay, so I'm going to put a -1 there and erase the rest. I cubed is I squared times I. If you think about that, I cubed is just I times itself 3 times, which is I times itself 2 times plus another 1 time. So I squared is -1, and I is I. So I've got -1 times I, or -I. I to the 4th is another important one. It's going to be, well, there's a couple of ways to do it, but I like I squared times I squared, which is -1 times -1, which is a negative times a negative is a positive. So we have I, -1, -I, and 1. Now that is the complete pattern, and I'm going to show you that it starts over. I to the 5th is I to the 4th times I, and I to the 4th is 1. 1 times I is I. So there, it's going to start over. If this said 5, 6, 7, and 8, I would just take this column and write it over there. It doesn't. But I to the 6th is I to the 4th, which is 1, times I squared, which is -1. So I've got 1 times -1 is -1. So the pattern is just I, -1, -I, and 1, and then it starts over. So this is equal to I to the 5th, this is equal to I to the 6th, I to the 7th, I to the 8th, and then it repeats I to the 9th, I to the 10th, etc. So if it's something low like I to the 15th, I could just keep counting. 11, 12, back to the top. 13, 14, 15. So I to the 15th is like I cubed, which is -I. Well, what happens if that number gets a little too big to count? You really want to count out 34 numbers and try not to, lose one, make a mistake? Well, one thing that, if you did do that, one thing that would keep you a little bit on track is that if that is even, look, if I has an even power, it's either 1 or -1, and if it has an odd power, it's either I or -I. But what you do is you see how many times it goes into 4, and see what the remainder is. And the remainder is the important part. It's either going to be a remainder of 1 here, 2, 3, or not 4. It's going to be more like I to the 0 power. 1, 2, 3, 4, which, by the way, is equal to 1. So I do the division. How many times does 4 go into 34? Well, 8 times 4 is 32, and that leaves 2 more. So it's 8 remainder of 2. The remainder is the key. That means it belongs in this family right here. So if I started counting out, I would have gotten to I to the 34th here. So it's -1. All right, now very seldom are we going to have to apply this, particularly since we're pretty late in the game, but the ones you really are going to have to know here is that I is the square root of -1. That is the definition. So this right here is really going to be important for us. Another one might be that I squared equals -1. So those are probably the 2 most important things to get out of this table. Alright, so an application, a simple application, the square root of 36. Well, what times itself is 36? That's 6. Now down here, the square root of 25. What times itself is 25? Well, if you think that the answer is -5, that's not true, because -5 times -5 is positive. negative 5 times negative 5 equals 25, that doesn't give you the negative 25, so that's just not true. So slash through that equal sign. But if you have negative 5i times negative 5i, I squared is negative 1, that means you have a negative 25. So it's really negative 5i. Well, here's another way to think that through. Negative 25 is negative 1 times 25. Each inside the square root. You can each give them their own square root. And so we have the square root of negative 1. Definition, square root of negative 1 is I, and the square root of 25 is 5. So that's I times 5. Now we typically are going to put the rational part in front of the imaginary part, and we say that we get 5i out of that. So our last one here is just a slight bit more complicated, but not too much. We're going to skip to this method. We're going to say that's negative 1 times 25 times 2. Why did I do 25? Because it's simplest radical form, and we are looking for perfect squares. So the square root of negative 1 is I, the square root of 25 is 5, and the square root of 2, 2 is not a perfect square, it doesn't have a pair, in fact it's prime, so it stays inside the radical. So if this said the square root of 50, like in our last section, simplest radical form, you should have come up with 5 radical 2. And the new thing that gets added is pretty simple. If it's a negative inside the radical, out comes an I. Now just like last time where I had the 5, it needs to go in front. I'm going to do that again here. So it's 5i radical 2. Alright, now how that is going to apply when we are solving quadratics and we end up having to take the square root of a negative, we can now go further. Let's see. I don't have any b terms, so b is 0, which means I can use inverse operations in all of these. That's what I'm going to do. Divide both sides by a negative 2. When I do, I get negative 9 equals n squared. Take the square root of both sides. When I do, I've got to put plus or minus. When I introduce a square root to cancel out a square, I've got to consider the positive and negative square root. So the square root and the square, they cancel each other out, and on this side I get n. Now on the other side, I've got the plus or minus still there. Now from the square root of a negative, I might say that's the square root of negative 1, and then the 9 gets its own radical. Square root of negative 1 is I. The square root of 9 is 3, and I'm just going to go ahead and put that in front of the I, so I've got a 3i. Bring down your plus or minus, and we're all set. Next one, subtract 1 from both sides, so I get x squared equals negative 7. Take the square root of both sides, and I get plus or minus the square root of negative 7. Now the negative is going to come out as an I, but 7 is prime, there are no perfect squares, and I get plus or minus I radical 7. Last one, add 2 to both sides, and I get 3y squared is equal to negative 8 plus 2 is negative 6. Divide by a positive 3, and I get a negative 2. Take the square root of both sides, and I've got plus or minus. I've got a negative inside the radical, so it's going to come out as an I. So I've got that I should go in front there. Let me get that. So I've got plus or minus I radical 2. Okay. Complex numbers. Complex numbers are in the form a plus bi. Now, you've seen this somewhat before. The part you've seen before is you've seen things with an a and a b, like ax squared plus bx plus c equals 0. A and b, just like last time, are going to represent any real numbers. The I is the imaginary number, so the bi is called the imaginary part, and the a is called the real part. So real part, include the b and the I together as the imaginary part. So some things we could do with this, and these are going to be some pretty easy things, particularly up top. We're going to add the real parts together, so the 4 and the 7 get added together, and that's 11. And then we're going to add the imaginary parts together, include the signs. I've got a negative 3 added to a positive 9, which is like 9 minus 3, so that is a positive 6i. So 11 plus 6i. In subtraction, what I would do is I would just say that we are going to distribute a negative 1 to this second complex number. So it's going to be negative 3, because negative 1 times 3 is negative 3, and then minus 7i. Or a negative times a positive is a negative, and negative is like subtraction. You can put that in parentheses if you would wish, put the plus sign in front of it. 5 minus 2i, and now just like last time, real added to real 5, add that to a negative 3, and I get a 2. A 2i, a negative 2i, plus a negative 7i is a negative 9i. Add two negatives together, the absolute value of that negative just gets larger. Negative 2 plus a negative 7 is negative 9. Attach the i's. Okay, now this, it is simple. It's got 0 for the real part. You can put that there or not. So, but if you're always worried about I need to add this a to this a, where's the a at? It could just be 0. So 0 plus 5 is 5. And then I got 4i minus 12i. So that's like 12 minus 4. 12, 11, 10, 9, 8. But the 12 had the higher absolute value and it's negative, so minus 8i. 5 minus 8i. Alright, the next one's pretty simple too. We're going to distribute the 4 into both those terms. A real number times a real number is still real. 4 times 3 is still 12, just like you always knew. Well, what happens with 4 times 5i? Well, you multiply the real part of that, 4, times the real portion of the bi, which is the b. 4 times 5 is 20, but we attach the I. Probably exactly what you expected. If that I was like an X, it would have been 20X, but it's an I, so it's 20I. Alright, so how is this any different at all? Well, it hardly seems any different so far. Like this feels like unlike terms. It is. But you're going to see something a little bit different in this problem here. And what you need to remember, I did say that the definition of I was pretty important. We've already used it plenty. But here's another one. I squared equals negative 1. You got to remember that. So if I multiply 3 times 3, I get 9. Multiply negative 2i times 3, I get negative 6i. And then I'm going to multiply 3 times 7i, and I will get 21i. It's positive, so plus. And then finally, and here it is, I've got a negative 2 times a positive 7. Well, that's a negative 14. I've got an I times an I. Well, that's an I squared, but I squared is negative 1. So this last term becomes real. A negative 2i times a positive 7i is going to turn out to be a positive 14. Negative 14 times negative 1, positive 14. Now I've got two sets of like terms to combine. I've got the 9 and the 14, add those together, 23. I've got the 21i plus a negative 6i, that's like 21 minus 6, attach the I. So that's going to be 15i. So 23 plus 15i. Okay, so pause this video and try these. Alright, I haven't finished this last one here, but hopefully you got these two right. Add a 2 and a 7, it's simply 9. Add a negative 5 to a negative 1, then you'll get a negative 6. Attach the I, so 9 minus 6i. Now, this one I could distribute, or I could think minus each time. 3 minus 5 is negative 2. 7 minus a negative 2i is like 7 plus 2i. And 7 plus 2, 9. Okay, this last one, I went and I drew a box. The new stuff is down here when you have your I squared. Negative 3 times, well, 1 is negative 3. I times I is I squared. And I'll have a negative 3 times a negative 1 is 3. 20 plus 3 is 23, so that is going to be my A. My B, take negative 12 and add 5, and so I'm going to get, what, negative 7? So minus 7i. I. Okay, we'll have some more problems to do on the next video.